Good day, I am Uwakwe. I'm glad to present my work as part of the Ruka Lab at the University of Connecticut. This work is on the design of an underactuated graph changing hand, which we have called the PhaseHand. In robot hands, if we want to increase the number of graphs a robot hand can perform, one thing we can do is to throw in more complexity by using more motors to make it more dexterous and have more independent movements. However, this uses a complex, heavy, and costly device. So the question is, how can we do this and at the same time reduce complexity? The IHY hand is underactuated and does move switching, as we can see here in this video, to perform the tripod, power, and pinch grabs. It uses 4 motors to close the fingers and 1 additional motor to change the grab style by rotating 2 fingers. An approach called underactuation has been introduced in robot hands, reducing the number of actuators and increasing the degrees of freedom, and this can also be achieved using differential mechanisms. Our solution is to apply underactuation to move switching as well rather than limit it to just the grabs itself. Our design is partially inspired by observations of the dactyl nature of the osprey's foot. At the bottom left here, we have a cartoonish representation of these configurations. In the video, there appears to be a consistent transition of the osprey's toes from a 3v1 to a 2v2 configuration. To simplify this further, we removed one of the digits to have a 3-finger robot hand, so we can have it in the full open configuration for a power grabs. Then have finger A swivel towards finger B for a tripod grabs. Then if finger A can close before the last 2, we can perform a pinch grabs using fingers B and C. This is our device, the PhaseHand. The hand weighs 330 grams and the fingertip aperture is 170 millimeters, approximately the size of a large human hand. It also uses only 1 actuator. Here we added an underactuated hinge at the base of one of the fingers, and through some tuning and careful heuristic selection of spring stiffnesses, we created a finger closing sequence to circle through the grabs. The swivel mechanism, that is the hinge, and finger A were coupled using springs of the same stiffness, K1 and K2, while fingers B and C were coupled using the same springs, but of higher stiffnesses, K3 and K4. Now, if this is so, and if the friction force is greater than the joint frictions, also leveraging the internal frictions of the springs, we can obtain a phase-changing hand. Using 1 actuator for the first mode, in the open configuration of the hand, we can perform a power grabs by leveraging on the friction between the palm and target object, so that the swivel mechanism will jam, preventing mode switching. For the second mode, we can perform a tripod grabs when we have a 2v1 configuration, after finger A has swiveled towards B and hit a hard stop. Lastly, since finger A closes before B and C, we can perform a pinch grabs using those 2. Now we demonstrate how this works using 4 objects of different geometries and weights. First, this Pringles can is grasped and picked up using the pinch grabs. Then this is also done using the tripod grabs. Because of the compliant nature of the piece of cloth, the hand passively adapts to it, picking it up. The pinch grab is also used here to pick up the whiteboard marker. For these particular grabs, the hand can either be preset to the desired mode or not, making it simple from a control perspective. And lastly, the power grabs was used to pick up a soft ball in the power mode. For our demonstrations, a grasp was considered successful when the object was firmly grasped, lifted to a height of 2 feet, and no slip recorded for about 5 seconds for 3 trials each. This graph shows the force extension profile of the phase hand using a load cell. At the initial phase, the hand is unactuated, so nothing happens. At phase 1, finger A swivels, hits a hard stop and begins to close. At phase 2, finger A is fully closed. At phase 3, fingers B and C close. We recorded a force of 85 newtons and total tendon travel length of 2.65 inches at full closure. We were able to achieve multiple discrete outputs using a single input, and also enable adaptive and compliant grasping with mechanical simplicity. Thank you.